we are going to take a look at some calculations using the icebox. It's the board problem on page 7 and 8 of your homework packet. So first thing, I'm given an equilibrium constant. I'm given an equilibrium equation. I think you can see that up here. And ultimately, let's see if I can move this up. There we go. So calculate the concentrations of each material present in each case having the following initial concentrations. So I kind of broke this down, and I'm told that this is going to be 1.0. We're going to assume that's molarity. This is 0. This is 0. In other words, if I don't have any of these products, I think I'm just going to put a line through here and draw this down right through the middle. So I only have reactants. I don't have products. And so the reaction is going to proceed from reactants from left to right in this case. So what's going to happen is it's going to lose an amount. We're going to call this X right here. And it's going to be in the same ratio here. So we're going to call this X here. Okay, I'll put a minus sign, or I'm sorry, a plus sign here. Okay, because what's going to happen is the IBR is going to break up into I2 and BR2. Am I going to get more I2 or BR2? The ratio is 1 to 1, so they're going to both be X. Notice this number is twice as big, so this is going to be a minus, and it's going to be a minus 2X right here because of the 2 to 1 to 1 ratio. So we're going to start at this point. Not all of it's going to react. If it all reacted, that's not what's going to be happening, and we could figure out our amounts from there. We'd probably have, half as much of each of these things, 0.5 and 0.5 and nothing here. But this goes in this direction, then it comes back and forth and establishes an equilibrium. In fact, if I look at the equilibrium constant, if this is a number smaller than 1, I'm guessing I'm going to probably have less products at the end and more reactants. So I don't think it's going to proceed all that far, but let's take a look. All right, so what is E going to be right here? It's going to be 1.0 minus 2X. Okay, so I'm going to try to draw that in here. Kind of wish I wouldn't have put that line through like that. 1.0, and I'm just going to erase this right here, and then I'll say minus 2X. And then this one is going to be, so we can still have our line, it'll just be a little curved. We still have X here, and we still have X here. Okay, I haven't talked so much about the icebox yet, but this stands for initial, this stands for change, this stands for N, and we're going to show how that's going to end up working for this problem. All right, given that, what I'm going to do is there is an equilibrium constant expression. I could write it here, or maybe I'm just going to write it down here, and that is K or Kc because it's a concentration. I think I'm just going to write K, and that equals the products over the reactants. So I got I2, and I think this is going to be a little bit easier to use this. I'm going to put this right here. I don't like where that is. Let's try this right here. I'm going to say it is, try one more time. I2, and that should be a subscript there. And then I'm going to put a concentration there. And then I'm going to say it is going to be BR2. And then I'll put that there. So these are the reactants. I2, there's a 1 coefficient, so I2 to the first power. Think of that 2 as a subscript. And then BR2, again, this 2 is a subscript to the first power. So that's right. And then I'm going to divide it by IBR. Because these are all aqueous solutions, we're going to include all these different terms. So I could type that in there, and I'm going to do that as, let's see, I'll type that box here, and we'll call that IBR. I'll put this bracket, and then I'm going to square that. I think I need to actually just show that. Why is it squared? Because the coefficient is 2 right there. So it's I2 concentration times this IBR, and that's working right here. Okay, so if I took this and plugged in these values, and I'm going to kind of come up here and show my work over here. K is 8.5 times 10 to the negative third. So I'm taking that K, and then what is I? It is X, and what is BR2? It's X. So it's not too difficult to see. I think that that would be X times X, or X squared. And then the last thing is IBR squared would be, IBR is 1 minus 2X, and that's in parentheses, and then I am going to square that. So where did I get this? I just substituted this 8.5 times 10 to the negative third for K, the 1.0 minus 2X for the IBR, and X in for here and X in for here, and came out with this. Now notice this is a perfect square. So even though this is some tedious algebra, it's not too bad because this is a perfect square. So I can just take the square root of both sides, and that gives me X over 1.0 minus 2X, and that gives you square root here, which is 0.092. Same thing here. I move this up into the numerator, and I get this, and ultimately I solve for X, and I get 0.078 molar. So I do the math, you can follow that. I get 0.078 molar. So that's what X is, okay? And so I'll make sure I'm doing this right. And that's what we're trying to find out. X would be the concentration of this. So we're gonna call this, okay, point, or zero, I'll just call it 0.078, and I'm gonna put a big M there. And then this one's going to be right here, 0.078, and put a big M here. And what is this one? It's going to be 1.0 minus 2 times point. So I'm going to say this is 1.0 minus 2 times 0.078. And so I'm plugging in for that. And then when I add that to there, it ends up being, the math, I think 0.84 something, or 0.84. So that's what we end up with right here. I think I'll just write that in. And this ends up being 1 minus 0.2078 is about 0.84 molar, okay? So notice it, if that's right, how much did it dissociate? Not that much. I mean, from 1 to 0.84, it looks like about, what, 16% of it went away. And then we formed these things right here. So, you know, certainly couldn't ignore this X. It's a pretty significant amount. Sometimes we'll be able to do that and take shortcuts, but not here. But we definitely have a lot more reactants and products if we look at these concentrations. So this would be my answer to this problem. I think it asks for the concentration of each thing. That is 0.84 molar, 0.078 molar here, and 0.078 molar here for each of these different columns. Can we check to make sure this is right? Yeah, let's just plug in these values, and it should come out to equal this right here. So I'm going to go ahead and do that, and I2 is 0.078. All right, so let's do this and say parentheses 0.078, and then times 0.078. That's going to be in the numerator. And then the denominator, draw a little line there. We're going to put the 0.84. So let's do that and say 0.84. And that's going to be squared. I'll just square that there. So do the math on that, and you punch that in, and you get, I think it's 8.6 times 10 to the negative third. So 8.6 times 10 to the negative third. Okay, so this should, when I go figure this out, now we don't do units on K, this should be the same as this or really close. And again, this can vary a little bit just because we're only doing 2 figures and it depends on your rounding. That certainly is very close. So I'm thinking I'm gonna have the right thing. So just going back and looking at this, okay, I'm using the icebox to solve this problem. I'm expecting, because of this K value is pretty low, I'm expecting it not to dissociate to a huge amount. And that's why my molarity on the reactant side is bigger than my molarity on the product side. So it seems to be matching what we have and what we'd anticipate right there. All right, take a look. A key is also posted, so you can just look at this and take a look through this. And then try number 2, keys posted, and then I have another video for number 3. Thanks.